In this video, we're going to derive the double angle identity for the cosine function. And there are really three double angle identities. The first one right here, cosine of twice theta equals cosine squared theta minus sine squared theta, is derived using the sum identity for the cosine function. So we're going to start off by deriving this first identity. And the sum identity for the cosine function says that the cosine of alpha plus beta is equal to the cosine of alpha times the cosine of beta. And when it's a plus, we get a minus right here in the identity. We get sine alpha times sine beta. And the key for the derivation is to understand that alpha can equal beta. There's nothing in the derivation for cosine of alpha plus beta that said alpha and beta can't be the same angle. In other words, if you think about the cosine of 90 degrees, we can rewrite the cosine of 90 degrees as the cosine of 45 degrees plus 45 degrees. So this would be a case where alpha plus beta was in a situation where alpha equaled beta equaled 45 degrees. So what we do to come up with the double angle identity for cosine is we do exactly that. We say let beta and alpha have the same measure. Let beta equal alpha. And then everywhere we see beta in the sum identity for cosine, we can replace it with alpha. So we make the replacement cosine alpha plus alpha equals cosine alpha cosine alpha minus sine alpha times sine alpha. And then we simplify things a little bit. So cosine of alpha plus alpha is cosine of twice alpha. Alpha plus alpha is 2 alpha. Cosine alpha times cosine alpha is cosine squared of alpha minus sine alpha times sine alpha is sine squared of alpha. And this establishes the first of the three double angle identities. To get the other two double angle identities, we use the first double angle identity in conjunction with the Pythagorean identity. So we remember that the sine squared of alpha plus the cosine squared of alpha is equal to 1 by the Pythagorean identity. And we could subtract the cosine squared from both sides, and if we did that, we would see that the sine squared of alpha was equal to 1 minus the cosine squared of alpha. Or we could just as easily, in the Pythagorean identity, subtract the sine squared of alpha from both sides, which would give us the relationship that the cosine squared of alpha has to be equal to 1 minus the sine squared of alpha. And either of these two relationships allow us to come into the first double angle identity for cosine and make some substitutions. So for example, I can rewrite the cosine of twice alpha equals cosine squared of alpha, but cosine squared of alpha can be replaced with 1 minus sine squared of alpha. So I make a substitution right here. I say, hey, you are the same as 1 minus the sine squared of alpha. And we already have a minus sine squared of alpha sitting here. So we simplify the statement and we get 1 minus. We're subtracting the sine squared of alpha 2 times. So we get minus 2 times the sine squared of alpha, which establishes this double angle identity. And the last double angle identity is derived in much the same way. We come back up to the original identity, which says cosine squared of alpha. Cosine of 2 alpha is cosine squared of alpha minus sine squared of alpha. But from this identity right here, I recognize that I can replace the sine squared with 1 minus the cosine squared. So I get, by substitution, cosine squared of alpha minus parentheses, replace sine squared with 1 minus the cosine squared of alpha, and distribute. So we get cosine squared alpha minus 1, minus minus we get plus, cosine squared of alpha, and we get the cosine squared of alpha being added 2 times, so we get 2 times the cosine squared of alpha minus 1 is equivalent to the cosine of twice alpha, which establishes the final double angle identity.